Welcome to octoScope's tutorial number 11. We appreciate you all joining, and we would like to, point out that this is the first one of our tutorials where we have actually done a part two. We had a lot of interest in our tutorial number 10, which is our mesh tutorial. And so we decided to dig a little deeper this time. So just by way of introduction, I'm Lee Chinitz, I'm the CTO at octoScope, and I am just the moderator for today. Our presenter is Janne Linkola, who is also the person who did the first of these mesh tutorials. Janne is our director of marketing here at octoScope, and he has a very unique background in terms of his ability to talk about this topic. Janne's worked for companies building Wi-Fi mesh products. He's worked for operators who are deploying Wi-Fi mesh, and he's now at a testing company which is enabling test tools for testing Wi-Fi mesh. So anyway, you'll soon hear from Janne. I am going to just mention one thing, which is that we have these tutorials, we do them live instead of just recording them and posting them, because we do like the interaction with the members of the audience. People ask good questions, and it's always very interesting to see what people are interested in. So we do encourage you to ask questions. There is a chat window at the bottom, which we'll monitor. There's a Q&A button that you can put your questions into. So however you'd like to do it, we would love to hear from you. And with that, let me turn the microphone over to Janne.
Thank you, Lee. Yes, as Lee mentioned, we're going to dig a little deeper into the Wi-Fi mesh because it's such a fascinating area. Of course, a very hot topic in our industry. There are lots and lots of products being sold both in the retail channel as well as through ISPs. There are some very significant investments that a few of the ISPs are making into this space to create products that better suit their needs. And it's also technically a very interesting topic for us engineers and testing people. Namely, the first time we have multiple Wi-Fi nodes in the home sort of interacting with each other to deliver the service. And this introduces all sorts of new challenges. The main thing being mobility, right? How should a station that is moving across the Wi-Fi network, how should it roam? This is a kind of a complicated problem, partially because in the self-forming phase of the Wi-Fi, there's usually one node that is directly connected to the internet, and maybe a one or two nodes that are directly connected to this root node, and there may be further nodes that are not connected to the root node directly, but use maybe one or even two further hops before they reach the internet. And so this, as you can imagine, leads to sending packets multiple times and impacts the user experience. And of course, the challenge is that traditionally in Wi-Fi, station is the only entity involved in making roaming decisions. Usually these algorithms are very, very simple. Basically, they just look at RSSI and kind of choose the best access point with the access point with the highest RSSI as being the one they connect to. Now, there's some, stickiness involved as well, and some stations are very sticky. But anyway, with mesh Wi-Fi, that logic is just not enough. We need to involve more complicated decision making, and there is this activity that we call steering, where the network itself can impact the roaming decisions because of the such a big difference that the number of hops between you and the internet causes. Now, how big are these impacts exactly is what our first demo is going to be about. What we're going to go through is the throughput impact, as well as the round-trip latency impact when you are connected directly to the node connected to the internet, or go through one extender or two extenders. The way we're going to do this demonstration is we have a 3-node mesh set up in an octoScope StackMax testbed. We have it set up like this here. And we're going to use an octoScope test instrument called StayPal. It is physically located here in a fourth chamber. And it sees the mesh network through 3 attenuators, 1 to each of the nodes. And the way we achieve the zero-hop case is we minimize the attenuator connecting the StayPal to the root node while maximizing the 2 other ones. And then correspondingly, the one-hop situation, we maximize that first extender and instead minimize an extender connecting the StayPal to the first extender. And then finally, the 2-hop case, and I'm guessing you're already guessing how it's done. So minimize this extender. This is the only extender that minimize this attenuator. The StayPal connects to the second extender, and through that, 2 hops, and he's in the internet. Let's look at what that is going to look like in practice. What I'm doing here is I'm connecting to an octoScope testbed using my web browser. All octoScope testbeds have a web-based user interface, and they can be connected to anywhere from the building or actually even anywhere from the world. They're completely location independent. And the user interface looks like this. We have sort of 2 sections here. The section here on the left is where I configure my test case. So I define traffic pairs, for example. I have 2 traffic pairs here defined, one for throughput and one for ping latency test. This same area has, you can configure your turntables, your sniffers. Importantly for this test case, I have all these attenuators here that interconnect the various chambers and instruments to each others. The attenuator between the station and the root is minimized here first. So the station is connected to the root node of the system. And here on the right, we see various real-time graphs plotted as the test case is progressing. The ones that we want to look at is throughput here, the RSSI as seen by the StayPal here, the ping latency as we observe it, as well as the phi rate between the StayPal and whatever access or node it's connected to. As you can see, the throughput through the root node is about, like 550 megabits per second. And we're seeing about a 50 millisecond latency here. Now, what I'm going to do next is I'm going to minimize the extender, the attenuator between the StayPal and the first extender. And so now the StayPal sees both the root node as well as the first extender. It's still connected to the root node because it has a great signal and there's no need here to do any kind of roaming event. But as I increase the attenuator between the station and the root node, we see a dip in the RSSI. I increased the attenuator by 28 dB. We see here a corresponding dip in the phi rate as well as the throughput went down. Interestingly, small impact already to the latency, not yet very dramatic. But as I continue increasing the attenuation between the station and the root node, we should be seeing a handover event here soon if things go according to the plan. And there you go, there it is. So as you can see, I maximized the attenuator between the station and the root. The only thing the station now sees is the first extender. And in fact, we're in great RSSI. But look what happened to the throughput. We were at about 550 megabits per second through the root. And now we're at maybe 200, maybe that's 230, 220, something like that. So the throughput has basically halved when we are using the first extender. Now, let's see what happened to the latency here. Now, unfortunately, we have a bit of a scaling issue here, but remember, we were at 50 milliseconds here in the beginning. If we zoom into this region that comes from the first extender, we'll see that the latency is actually about 100 milliseconds, but perhaps actually a little bit more. So basically, the throughput halved and the round-trip latency doubled. Now, what I'll do next is I will connect the stay-pal, or I'll minimize the attenuation between the stay-pal and the second extender, and I'll add some attenuation between the stay-pal and the first extender. And what we should see is a dip in RSSI here, because the first extender was very weak now, and we saw a handover event. We're now back at great RSSI. It means that we must be connected to the second extender. I'll just maximize the attenuation here to the first extender, just to make sure that we don't get any leakage in the system. And as you can see, the throughput again roughly halved. Now we are at a little over 100 megabits per second. And it looks like also there was an impact in the round-trip latency. Remember, we were at 50 here in the beginning, a little over 100 with the first hop. And now with the second hop, we are seeing a round-trip latency of about 200 milliseconds. So that's very interesting. Basically, we see that the impact to the user experience from these increasing amount of hops is actually quite dramatic. I mean, we can basically, a rule of thumb is the throughput goes down in half as you increase a hop, and the round-trip latency about doubles. Now, this is not the only factor that affects what kind of user experience you might expect from a mesh. Of course, there are a number of other factors. I'm listing here a few. Of course, loading of each mesh node affects how fast they can serve me. Throughput across each backhaul link. Some extenders may be further away from the root node than others. And of course, there are, let's say, more complicated airlink efficiency related considerations. As you know, the PHY rate in Wi-Fi adapts quite aggressively. And so the closer I am to the access point that's serving me, the higher PHY rate I have. And that means that I'm using less airtime for that data transmission. And that frees up airtime for other stations in the mesh and actually in the environment. So there's all these considerations. And now a simple RSSI-based roaming algorithm that's sort of traditionally implemented in stations is not going to capture much of that complexity. Now, let's look at the situation from the mesh network's point of view. The mesh network went through the self-forming phase, so it knows exactly which of these nodes is the root node. It knows which of the extenders are connected through one hop to the root node, and it knows which of the extenders have two or even more hops. So clearly, it knows a lot more about this situation, and it can affect this roaming behavior through the steering mechanism that I already mentioned. In 802.11v, we have this message called BSS transition management request, which the mesh network can use to issue to the station a request to roam. Now, of course, the mesh network can also know many of these other considerations. It certainly would know what the loading in each mesh node is, and it would know the throughput roughly in each of the backhauls. It also has a mechanism provided by 802.11k called Beacon Report, which is relatively widely implemented in handsets. This is a mechanism for the access point to ask the station's point of view how it sees the various access points. It's basically, can you give me the RSSIs of all these access points in the mesh? And it can take that into further consideration when it's making its steering decisions. Now, these steering algorithms are all proprietary. They're kind of trade secret. Not a lot is talked about these algorithms. They're certainly not standardized. And our point of view and experience is that they tend not to be yet fully optimized for all the usage scenarios that are out there. There's quite a lot of room for improvement we've seen. And so we've thought sort of long and hard about what we could do as a test vendor to aid people in testing these steering algorithms. So in our last tutorial, we showed you a brand new product that we had developed.
I'm sorry, Janne, we have a question.
Oh, sure, yeah.
They're asking, how much does latency correlate with throughput independent of number of hops?
Well, does latency correlate with throughput independent of number of hops? That's an interesting question. Lee, do you have a point of view to that?
Well, it certainly does. Depending on how, especially the length of the link, right? I mean, if you do like a TCP connection, over a lot of the internet, and you have high latency, you'll definitely get much lower throughput. And there are equations that describe this, based on what TCP is doing. I think in general, although I can't say for certain, the likelihood is that, if you're having high latency, then you're probably getting, packets that are delayed, obviously, somewhere in the network, and that's going to start causing packets to back up somewhere, right? And then typically that's what will affect your throughput, right? So if you have high enough latency that you start having buffer overruns, right? Packets back up somewhere, they overflow the buffers. Eventually, the system will decide it just has to get rid of some packets, and that will have to be retried, and that will cause the throughput to go down. I think that's generally the kind of effect when you're looking at latency and throughput together.
Oh, I'm glad to have Lee as a backup. That was a tough one. All right, let's go back.
Oh, I'm sorry. We have one more. We have a raised hand.
Oh, sure.
Go ahead, Matt.
Oh, and by the way, Matt saying it depends on source of latency. I think that's kind of what I was saying. Oh, it's Craig and Matt. Hi, Craig and Matt. So yes, it would depend on the source of the latency. Like I said, if the latency is being caused by what I said, then I think it would drive the throughput down. There may be other, just a long distance, for example, may not.
Sure. So we had a raised hand.
Yeah, that was kind of my point. If it's an RSSI problem, it's one thing. If it's a buffer situation, it's another. So to say that it directly correlates, I think that it's iffy. It's not quite as clear cut as it is with the mesh.
Right. Yes. All right. Well, look, let's move on. So as I mentioned, testing of the steering algorithms is kind of one of the key things that we want to test in a mesh network. And we want to make sure that these test scenarios that we expose the stations and the mesh networks to are realistic, that they're representative of something that would actually happen in the real world. Because, the real world is basically more complicated than anything that most people can think of. So we developed this tracker product, which is a field to lab replay style product, which allows us to basically record motion profiles in the field and then play these motion profiles back in the test bed while performing tests, roaming, steering, what have you, on stations and mesh networks. And we're going to show you a variant of the demo that we showed in the last tutorial. This is a 3-node mesh version of the demo, but just to set things up, so we set up a 3-node mesh in a 2-story home here in the Boston area, 1 node in each floor, including the basement. And then what we did is we took our FieldPal test instrument and we walked from the basement, took the stairs to the first floor, walked inside the first floor, took the stairs to the second floor, and ended up in the opposite corner of the house on the second floor. And basically got a recording like this out of the FieldPal. Now, we're illustrating this as in terms of RSSI here, but really you should think of this as a path loss measurement. And the time flows here from left to right, and obviously when we were in the basement close to the root node, then the signal from that root node was the strongest. And as we walked through the first and the second floor, then the extenders on those floors were strongest as we walk past them. Now, we have a 3-node mesh, the same 3-node mesh set up here in our test bed. We're using recordings from the field to set the path loss between the root and all the other nodes. So the mesh experiences itself in this test bed just like it would experience itself if it was in the home. Now, and we use these 3 recordings to each of the nodes to then drive each of the 3 attenuators that connect the StayPal to the mesh network. And of course, we're looking at, how well the mesh network steers us, because we've configured the StayPal to be a fairly passive entity in this test. It doesn't really like to roam much here. Any roaming event that we'll see is basically caused by the mesh network itself. So let's look at what running a test like that would look like in the octoScope testbed. So I'm going here to our script runner. This is obviously a slightly more complicated test, so it's not going to be able to do it manually like I did the previous run. But what I still am able to do is I'm going to be able to monitor the progress of the test here in real time through the octoScope UI, even though actually scripts are running the test. Now, same statistics here as before. And as I mentioned, the walk starts from the basement close to the root node. So we're seeing the same 550-ish megabits per second throughput through that root node. And now what we're seeing here is the RSSI starts to dip as we sort of virtually walk through this house now. We are probably taking the stairs here towards the first floor. And here we see the first steering event. We got suddenly a very good RSSI here. Can really only mean that we were steered to the extender by the mesh networks. And as you can see, we get the 250 megabit per second speed that we saw on the previous demo, right? So everything's consistent here so far. The walk continues. We were probably walked past the extender on the first floor here. That's why the steering event. And we are moving forward through the stairs to the second floor, and then the furthest point on the second floor. The mesh network, it's basically doing its thing. We don't really control anything here. We just provide the environment for the mesh network to do what it thinks is the best thing for the station. And this is a really cool way to see how those algorithms work. What happens here about 1/20 mark is we've reached in our walk the furthest point on the second floor, and what we now do is we play the recording in reverse. So we end up walking back through the first floor, and ultimately we'll end up back in the basement, and we'll see what happens here as how the mesh network basically reacts to that experience. And interestingly, we see probably a little bit of an anomaly here, right? We know that we are here back to the first floor and probably soon in the basement, but we got this region with quite poor throughput. So something to investigate further with whoever developed this system, whether it's an internal software team or maybe an outside vendor. Seems like we are potentially connected to one of the extenders here. And here, I think, is where we are finally steered back to the root node. The walk has progressed enough that we came back to the basement, and now we get this good RSSI here. And we're back to that 550 megabit per second speed that we saw in the beginning of the walk. So there you go, a live test of a virtual walk through a house with 3 mesh nodes. Now, what's really important to understand about this testing capability is that we can do that test over and over again, and basically expose, perform this virtual walk with the station across the house, and see if for example, if the mesh network does the same kind of steers every time. And in fact, you're looking at a superimposed image of 9 such tests. As you can see, of course, when we start the walk, we're by the root, so we get connected there, and as long as there are no roaming candidates available here, we get a very consistent throughput measurement. So clearly, the test bed is able to basically, measure the user experience well and consistently from run to run. But as we come to the first floor and we start seeing some roaming candidates, in some runs, the mesh network steers us one way, in some runs another way, perhaps doesn't steer us at all. And as we enter the second floor, even more variance can be seen in throughput measurements run to run. And this section here, as we walk back to the basement, is particularly, you could almost call this ugly, right? Clearly, the root node becomes available fairly quickly, and we could be steered there, and sometimes we are quite quickly, but on other runs, it takes up to a minute or even more before we're steered there. Now, in some cases, it looks like we looked at a couple of these on trace. We were band steered to 2.4 gigahertz. So we might have been steered to the root node, but basically on the wrong band, which is very peculiar, right? Of course, we could be taking traces here with our synchro sniffing technology to analyze this further, maybe give a trace to the software teams that were available. You might know that we have our synchro sniffing technology allows basically multiple probes in multiple different locations and multiple different bands and channels to capture simultaneous traces, and we're able to combine those traces into a single trace file for further troubleshooting. But anyway, perhaps, that's really the end of my material. Let's see if there's more questions.
Here's a question. Some of the anomalous behavior may be due to the client making roaming decisions and ignoring the steering algorithms. the comment.
It can be, yes. Now, our stay pal, which we used in that test, as I mentioned, maybe I didn't spend enough time on it, but we can configure the roaming threshold, and in this type of testing, it's useful to basically make it as passive as possible. So it wasn't really making any roaming decisions in that run or in those 9 runs. And furthermore, the implementation of 802.11v in it is such that every time it gets a steering request, it will always follow. So in this way, when you configure our stay pal in that fashion, then we basically expose the steering algorithm of the mesh network under test. But we could configure it differently as well if we wanted to, look at more complicated interactions.
Yeah, House just responds back to you that in the real world, this happens all the time.
Yeah, of course. Yeah. There's some vendors that are very famous for not taking steering. Well, either they don't support the protocol at all, or they, only follow very selectively.
So while maybe other people think of some questions, if they have them, let's talk a little bit, if you would like to. Oh, wait, hold on. I don't have to do anything. We got plenty of questions. Matt, what about the location of the extenders? That would likely change for different systems. And he makes the comment, I also assume that you can vary that in the chamber.
Yes, we can. Yes, that's a very good question. So as I mentioned when I was talking through this slide here is we, in our demo, we used the real life recording. We recorded also the path loss between each, the internode path loss basically in the mesh. Now, of course, so in that way, we got that configuration, whatever configuration I had the mesh set up when I performed that recording, was captured. Right now, you could say, well, maybe there's a mesh technology that has, I don't know, particularly powerful radios or something, and it would really be advantageous to locate them slightly differently. There is no practical node limit when we perform this type of recording. We could have more than 3 locations captured when we perform this path loss measurement. We could have, let's say, alternate locations for the 2 other nodes, maybe a little bit closer away to simulate, mesh networks that don't have particularly strong radios, and maybe a little bit further away for the type of testing that has better radios. So in that way, we could play with the impact of the location of the nodes. That's actually a very important test case to think through, because I'll tell you this, having worked at an ISP in this area, consumers tend to place extenders very, very poorly. I mean, typically the logic goes like this, right? Okay, my coverage is pretty bad in my master bedroom, so let me put an extender into the master bedroom. That's how most people think, right? As Wi-Fi people, we know that really what you want to do is probably put the extender sort of maybe halfway in between your master bedroom and wherever the source of the internet is. But that's so there's a lot of unoptimal placement of extenders, and we want to actually test that, because it's a realistic usage scenario that we might come across, and maybe the mesh network works perfectly when the nodes are perfectly positioned next to each other, but it falls on its face when there's a little bit of a, let's say, suboptimal placement of the nodes.
Yeah, so you're in trouble now, because you started talking about test houses, and you have Craig Smith on the line. So here we go. So Craig wants to know, what's the square footage of your test house, and how did you determine the node placement?
So the square footage, I think it's about 4,000 or so raw square foot, but the basement is uninhabitable, so it's technically, I think it qualifies like 2,800 or 3,000. So it was not huge, but sort of perhaps slightly larger than the average. And I placed the nodes. Really, they were on top of each other's on each of the floors. So what I did is wherever I put the mesh node in the basement, then I put the extender on the first floor above that, and then the extender on the second floor above that, roughly. Now, to the degree that the room arrangement allowed for that, but that's how I did it. I was really optimizing, making sure that the RSSI on the back hall is as optimal as can be.
I don't know if you want to make the comment that you often make and you haven't made right now about how users sometimes place them into suboptimal locations based on where they have poor coverage.
Yeah. Well, I kind of talked that through a couple minutes ago. Yeah. So yeah, that's quite often happens. Yeah, but people are notoriously bad at placing them, and that's why. In sort of advanced mesh systems, you often have all these, wizards that help you in placing, but people don't really follow that advice super well.
Would it be worth talking a little bit about, other things? So we've shown now how we can emulate different attenuation conditions between the station and the mesh, and also between the mesh nodes. Would it be worth talking about other things that might have an impact on how the device performs and where it gets moved to, things like congestion or interference?
Yeah. So of course we talked a little bit about a few parameters. It's a very complicated topic. Of course, interference is one really interesting one, right? Because maybe I'll use this slide to talk that through. So, especially when you have tri-band devices and there is a sort of a true option as to what band or what channel to connect to. Then interference and congestion on one channel might affect this algorithm. And of course, in a test bed like this, testing for that is relatively simple, right? We have all these extra test instruments that we can add to the test measurement. We have a test instrument specifically whose only purpose is to generate interference. It's called the iGen, the interference generator, and it can either play back PCAP files, that you capture from the field, and inject that into the test scenario in a controlled fashion, or it can also emulate non-Wi-Fi interferers, microwave ovens, Bluetooth, what have you. A lot of people use it to emulate weather radar events, which is important for DFS related testing. So yeah, so you can inject all of this into the test scenario, and let's say your expected behavior is that a steer happens to another channel, then you would be able to test for that.
And I guess while we wait just to see if there's any final questions, would you want to touch a little bit on anything we know about standards activities around mesh testing?
Yes, and you happen to probably be the better expert on this than I am, but
but you're the one talking, so.
Yes, exactly. Well, yes. So maybe you want to touch upon a little bit about the TR398 issue too, right? Broadband Forum has started this activity where they have published a test specification testing access points, and I think there's some interesting progress there.
Right. So great. So I asked myself a question. The reason I bring it up is that people do come to octoScope to find out about the best ways of testing functionality, across a range of different features and like mesh. But another thing that we find a lot of customers are very interested in is what the industry as a whole is looking at in terms of, a specific sort of performance metric. Now about 2 years ago or so, the Broadband Forum started an effort to do performance characterization of Wi-Fi with their TR398 specification. And the initial specification focused on, residential devices, and it was fairly straightforward. It was a single access point handling one or more clients. Obviously, for the same reason we're talking about it today, there's quite a bit of interest in multi-AP solutions. And so with TR398 issue 2, which is on the verge of being released, it should be released either at the very end of this year or very early in 2021. There's a first step towards looking at now, multi-AP tests. So they're tests having to do with repeaters, so throughput and repeated situation, and a roaming test where device will move from one device to another. So we are starting to see the industry, coming together and starting to think about how best to create performance tests that can be used to benchmark the performance of systems against each other.
Yeah, I think safe to say, as far as the mesh testing is concerned, that work is very preliminary. I don't think it's published yet, and even all the indications are that the first version will be a kind of a light touch in this topic. We went a lot further in this tutorial than I think they will go, but of course, looking forward, for us, it's these type of activities are ultimately a great help, because further consensus in testing methodologies helps everybody.
All right, I think we've
It looks like you had a follow-up question from Craig.
Did we have one? Sorry,
Yeah.
how did I miss that?
Do the StatePal's roaming modes allow for all specs that are supported in retail clients?
So yes. So the question is, the StatePal is our test instrument that is basically a station in our testing, and it does support all the relevant 802.11k messages as well as V messages, and I think it supports R as well. So yeah, it's a very good instrument for mesh testing. But if there's some specific input, we'd like to hear about it, of course. Knowing that this is Craig.
All right. Okay, so with that one, we'll start wrapping up. Again, if people have questions, feel free to let us know. And if you have questions after this, or if you're listening to this in its recorded version, you have questions, definitely reach out, contact us. We're happy to answer those questions. We may be reaching out to you to see what you think of these. We're interested in feedback, and certainly in any other topics you'd like us to discuss. So with that, I think I'll hand it back to you, Yanni, to just wrap it up.
Yeah, just reminding everybody that we record these tutorials on YouTube, and they're available there for later watching. Thank you, everybody.